Here are a couple of more Graham's law problems. This first one, a balloon is inflated with an unknown gas, stays inflated 2.83 times longer than a helium balloon that contains the same number of moles. What's the molar mass of the unknown gas? So we're going to set this up using Graham's law. So Graham's law, of course, velocity A over B is equal to the square root of the molar mass of B over A. Okay, so we need to decide which one we want to make B, which one we want to make A, and we also need to decide the significance of this 2.83 times longer. So let's think about what do you think that means, that the gas stays inflated 2.83 times longer? What can we then assume about the speed of that unknown gas? Okay, so if the balloon stayed inflated 2.83 times longer, then that means that that gas is moving slower because it effused slower, 2.83 times slower. Or, in terms of velocity, since it's moving, the unknown gas is 2.83 times slower than the helium, that means the helium is 2.83 times faster than the unknown gas. So even though the 2.83 is in the question connected to the unknown gas, because it's describing time, and time is inversely related to speed, the 2.83 can then be used as the relative velocity of the helium. So I'm going to say 2.83 over 1 is equal to square root of the molar mass, and then because He is my relative velocity of helium, its mass, which is pretty much exactly 4 AMU, is going to go on the bottom, and we're going to solve for the molar mass of the unknown on top. Okay, and so there we have it. Just had to square both sides to get rid of the square root to solve for x, and then once we do that, multiply both sides by 4 AMU, because that's in the denominator, and we should get about 32.04 AMU. Sig figs for these questions. Well, actually, I should amend my answer. 2.83 only has 3 sig figs, and that would have been the only measured number here, so it should have been 32.0 AMU. So this is actually pretty close to the molar mass of oxygen, so this might have been oxygen that was in the other balloon. Let's try another question. 4.83 milliliters of an unknown gas effuses through a hole in a container in the same amount of time. It takes 9.23 milliliters of of argon to effuse through the same hole under the same conditions. What's the molar mass of the unknown gas? So volumes are given, but volume depends on amount of gas. So what we're saying is one of them had a volume of 4.83 effusing out of a hole in the container. The other one was 9.23. So one of them, quite a bit more of the gas escaped. So the volumes in this case can be taken as speeds, as relative velocities. So the first gas, the 4.83 milliliters, would become, the volume of gas that's able to escape would become, would be directly related to how fast the gas was moving. So we're, that becomes its velocity instead of its volume. V stands for both, but we're gonna just ignore the milliliter part and call this its velocity, because the faster the gas is moving, the more volume will be able to escape. And we'll do the same thing with the other one. We're going to ignore the milliliters, and we're going to call this a velocity, 9.23. Because faster moving gas, you'd be able to, you'd have more volume of that gas effusing in a set period of time. So if we set this up, it doesn't really matter which one we make A and which one we make B. So if I just take, let's go ahead and we'll make this one A. Probably ought to be consistent with my color. And this one B. Then it's going to end up being 4.83 over 9.23. And then the argon is the one that's associated with the 9.23, so its molar mass, which argon is about 39.95 AMU, would go on top, and then the unknown would go on the bottom. So just going to try to solve for x here, see what molar mass you get. Okay, so there you can see my answer and my work. Once again, trying to solve for x, we had to square both sides to get rid of the square root. And then I got this, I want to do the division and then square. I get 0.2738 equals 39.95 over x. I just went ahead and put that over 1 so I could cross multiply 39.95 times 1 divided by 0.2738. If you wanted to do it the long way, multiply both sides by x, then divide by, it's the same thing. You're dividing 39.95 by 0.2738. We should get 145.89, or rounded to 3 sig figs, 146, which makes sense because less of it was able to escape a hole in its container in a given period of time compared to the argon, which means it must have been moving slower, which must make it a bigger, heavier gas. All right, so one more question. So, given volume of nitrogen required 68.3 seconds to effuse from a hole in a chamber. Under the same conditions, it took 85.6 seconds for the same volume of another gas to effuse. What is the molecular mass of this gas? So, what I want you to think about now is, if we're given times, is that directly related to velocity? We know we can use those numbers for velocity A and velocity B, but are we going to flip-flop them because time is inversely related to velocity, or are we going to keep them associated with the gases that they are with currently because time is directly related to velocity? In other words, is 68.3 going to be my velocity of nitrogen, or am I going to flip-flop it so that the 68.3 becomes the velocity of the unknown gas and the 85.6 becomes the velocity of the nitrogen? So is time directly or inversely related to velocity? Okay, so you should have said inversely, right? So nitrogen took longer. That means nitrogen is slower. So what I'm going to do is start setting up my math here with 68.3, my relative velocity, not for nitrogen, but for the other gas. All right, and then 85.6 is my relative velocity of the nitrogen. The nitrogen was able to effuse quicker. That means the nitrogen is faster. That's why the nitrogen gets the bigger number for velocity. So go ahead and see if you can finish the problem and get an answer. Okay, so there you go. Once again, we're solving for molar mass. And so if I had 68.3 on top, that was the relative velocity of the unknown, so that's why x is on bottom. The relative velocity of nitrogen on the bottom over here means its molar mass is on top. Square both sides, and then just divide 28.02 by 0.6366, and I get 44 AMU. So should make sense. It's a somewhat heavier gas, so it's going to take a little bit more time to effuse, 85.6 seconds, which is what the problem told us.